Welcome to Mrs. Z's Chemistry AP version. This is a continuation of the titration concepts worksheet. We're going to look at the fourth chart that we have in that worksheet where we are using a 25 milliliter sample of benzoic acid, a 0.1 molarity solution, and it's titrated with a 0.1 molarity solution of sodium hydroxide, the NaOH, and the titration curve below was generated. So this is the first example in this worksheet where we have a weak acid and a strong base. All the rest were strong and strong. All right, so number 17 says, calculate the pH at various points in the titration and enter your answers in the data table provided. Plot the points on the titration curve. Let's actually go to question 18 first here. Write a balanced molecular and net ionic equation for the reaction, and you can represent the acid as HA. So that's what I have here. HA, this is a weak acid, remember? So that means the A and the H are very attracted to each other. Very few of those H's get transferred to the base. But we do have a strong base here. And so the products, we probably should write this as a double arrow here. But the products are NaA, where the A represents the conjugate base of the acid here, and then water. And this is the molecular equation that we have here. And then here's the net ionic equation. The only thing that we can cancel is the Na. And the reason for that is we can't cancel this A because it's very attracted to the H, to the acidic hydrogen. In the strong acid, we could cancel the A because all of it dissociates from the hydrogen. For here, though, very few of them dissociate from the hydrogen, so the only thing we get to cancel is the Na. I also wrote it out with the actual acid because I think it's easier to see, and it's not too hard. This was only said because this is a very long conjugate base. Well, but here you have the weak acid reacting with the strong base, NaOH, and then it turns into this, where you have this part is the conjugate base with a negative charge, and then here's your Na with its positive charge. So that's the salt that was created. And then water, of course. So then the net ionic equation is everything written without the Na, though. So we have our weak acid, we have the hydroxide from sodium hydroxide, we have just the conjugate base by itself, and then we have water. I also looked up the Ka for this, 6.3 times 10 to the negative 5. This is the ionization constant or acid dissociation constant for benzoic acid. It is going to be needed in this problem, so I feel like it should have been written in the worksheet, but I looked it up for us. All right, so let's go back to problem 17 where it says calculate the pH at various points. The first box here is after 0, NaOH has been added. So all we have is a 25 milliliter sample of 0.1 molarity benzoic acid. So this question right here, where it says before NaOH has been added, calculate the pH of a 0.1 molarity benzoic acid solution. This is the type of question that I taught and tested on in honors chemistry, so don't overthink this one. We have the general reaction or equation of Ka is equal to x squared over A minus x, because this is what you would get in the ice table, where x is equal to H3O or H plus, and A is equal to the concentration of the weak acid. And you get to ignore x in the denominator because it is so small that A minus x is still A when you round to significant figures. So let's go ahead and solve this. We have our Ka, 6.3 times 10 to the negative 5, and that is equal to x squared over A, and we're going to ignore the x in the denominator. So we have 0.10. This right here is A. It's the concentration of the weak acid. So when we solve this, x then, you can pause and solve this if you'd like, but I solved it for us. X is 0.00251, if we're going to round it to 3 significant figures here. That is H3O, so then when we take the negative log of that, that gets us the pH. So then pH is equal to 2.60. Remember that because this is 2 significant figures, and this is 2 significant figures, our end answer should be in 2 sig figs. Before we get to the end, though, we shouldn't round. We should round at least to 3 or more. So remember that in pH or POH or anything, when you take the negative log like pKa or pKb, the significant figures is are only the ones after the decimal place. So 2.60 is technically only 2 sig figs. That's the answer that we put here, 2.60. We can also double check on the chart that here, here we have 2, this would be 3, this is 2.5, so yeah, it looks like it's starting out at 2.6. All right, now let's go ahead and start. This ice table that I have written in the text here is for after we've added 2 milliliters of sodium hydroxide, which is the pH we're going to try to find after we've only added 2 milliliters. So in this ice table, we need to include the conjugate base. It is going to be very important for this in solving the pH, as you'll see in a moment. So initially, we have a 0.1 molarity solution of the benzoic acid, and we have 25 milliliters, or 0.025 liters. So initially, we have this many moles. So we're going to write that in here. Do the entire ice table in moles again. So then we have 0.1 molarity of the sodium hydroxide given in the problem. We have now added only 2 milliliters or 0.002 liters to give us this many moles of hydroxide that's coming from the sodium hydroxide. And we have 0 of the conjugate base initially because this is on the product side. Then the change row is going to have to be the sodium hydroxide number because that is the limiting reactant. So we're going to fill this in here. We have 0.0002. This is a subtraction sign here. And then we're going to add 0.0002. Notice that from the chemical reaction here, there's a coefficient of 1, 1 to 1. So the change row, every number in the change row should be the same. Just subtracting for the reactants and adding for the product. So this is going to be a 0. The leftover hydrogen ions is 0.0023. And then, of course, we have 0.0002. Now, I added one more row in the ice table, and this M just means molarity because when we solve for pH, we need the molarities of each of these. So the total volume is the 25 milliliters plus the 2 milliliters. This is for the acid, this is for the base. When we add that, that's 27 milliliters or 0.027 liters. So here we have moles divided by liters, and we get 0.085185. And yes, that's a ridiculous amount of numbers, but we're just going to use them for the sake of it. We have 0 sodium hydroxide left over. Then we take moles divided by the total liters, and our conjugate base has a molarity of 0.007407. All right, here is where solving for pH is different. When you have the strong acid, strong base, you just take the negative log of this, because whatever your weak, or whatever the concentration your strong acid is, that's the concentration of your H3O or H+. But with the weak acids, that is not true. So we have to recognize that this is a buffer. A buffer is when a weak acid is mixed with a strong base and the weak acid is in excess. And that is exactly what we have here. Weak acid reacted with a strong base. The weak acid is in excess. The strong base ran out first. This is a buffer. You can also realize that a buffer is when you have a weak acid and its conjugate base in large amounts in the solution. If all you had was just a weak acid dissolved in water and you don't mix it with anything else, yes, you technically have a weak acid and its conjugate base, but because weak acids dissociate so little, the amount of conjugate base you have is not very much. But when you've mixed in some sodium hydroxide, we now do have a significant amount of conjugate base. So this is a solution of a weak acid with its conjugate base. That is a buffer. Here's the important part. The pH of a buffer depends on the concentration of the weak acid, its conjugate base, and the Ka of this weak acid. And it's put all together in this lovely equation called the Henderson-Hasselbalch equation, where you have the pH is equal to the pKa, which is the negative log of your Ka, and you're going to add that to the log of the conjugate base divided by the weak acid. So let's go ahead and plug this in. Here is the Ka up here. We're going to take the negative log of that, and we're going to get 4.201. We're going to add that to the log of the concentration of the conjugate base, which is this one, 0.007407. Note that this must be concentration. These brackets means concentration. You cannot use moles. You have to use the concentration. The HA is our weak acid here. 0.085185. All right, when we solve this, we get pH. Oops, let's erase this. We get pH, which is 3.140. 2 sig figs is just the last two here. So we can add that up here, 3.14. All right, following that same procedure, I want you to fill out this ice table or just do the calculations that you are needed using the Henderson-Hasselbalch equation, but for when you add 12.5 milliliters of sodium hydroxide. Pause and work that out. All right, so here is the filled-in ice table with the amount of moles of sodium hydroxide from the 12.5 milliliters, the new total volume. Here's the whole ice table. Pause and see if this makes sense and what you wrote down on your own. The molarity now is this and this. So the pH of the buffer here, because this is a buffer, and I'm going to repeat this because it's so important. When a weak acid is mixed with a strong base, and the weak acid is in excess, that is a buffer. The pH of a buffer depends on the concentration of the weak acid, its conjugate base, and the Ka of that weak acid. And we have this equation. pH is equal to pKa plus the log of A minus over HA. Notice if you put this 0.033 divided by 0.033, that's 1. So when you take the log of 1, you get 0. So when the weak acid and its conjugate base are equal in concentration, the pH is equal to the pKa of the conjugate acid, or of the weak acid. So that means the pH is 4.201. Now, in a later question, I think it's just question 19 on this worksheet, it says examine the pH after 12.5 milliliters of NaOH was added. What is special about this point of the titration? And mark this point on the titration curve. Well, let's go ahead and do that. So 12.5 would be right here. And notice that at the end point, that's at 25 milliliters. So what is special about this is that this is the half equivalence point. Half equivalence point. We have added exactly half the volume that we need in order to get to the equivalence point. At the half equivalence point, this is important right here. pH is equal to pKa. And that is from the Henderson-Hasselbalch equation. And that is because the log term of this equation is equal to 0. So then the other thing that is true is that the weak acid is equal to its conjugate base at this point. We have titrated enough so that this is true. The weak acid is equal to the conjugate base, and the pH is equal to pKa, and this all happens at the half equivalence point. So that is what is needed from question 19. All right, so now we are going to move on to after you've added 22 milliliters of NaOH. Oh wait, we can add in our pH up here. So this is the 4.20. Now I want you to solve this on your own. Pause and work this out. All right, so here is my filled out ice table for after we've added 22 milliliters of NaOH. That gives us 0.0022 moles of NaOH, which goes here. The total volume is now this. When you fill out the ice table, pause to see if this makes sense. And now we have the molarities given here. This is still before the equivalence point. Okay, I'm going to repeat it again because it's that important. This is what a buffer is. When a weak acid is mixed with a strong base, and the weak acid is in excess. That is still true from looking at the ice table. Our strong base ran out first, and our weak acid is in excess. A buffer is when you have a weak acid and its conjugate base mixed in solution. The buffer, pH, depends on the concentration of the weak acid, the concentration of its conjugate base, and the Ka of the weak acid. Here's the equation. We plug in our values, and we now get a pH of 5.07. Let's add this here. Oops, up here, 5.07. All right, now we have left with the 25 milliliters, and we know that this is at the equivalence point. You can mark that on your graph here. So we have roughly right in between is like roughly right here. This is the equivalence point. I'm going to work this through because it's a little bit different in trying to solve the pH here. So we've added 25 milliliters of NaOH. We now have this amount. So we have our initial, and our initial conjugate base is 0. Both of the weak acid and the strong base run out at the same time, and all we have left is conjugate base when we get to the molarity. So the buffer happens when a weak acid is mixed with a strong base and the weak acid is in excess, but that really no longer is the case here. The weak acid is not in excess. Neither one is in excess. So we actually can't use this equation because it's not really a buffer anymore. This equation only is used when we have a buffer. So we actually have to write out another ice table. In reality, you could just jump to this calculation here once you understand what's going on, but I want to show the ice table so we can see what's happening. This conjugate base right here is very attracted to hydrogens because, well, it's a weak acid. That's the whole point. The weak acid very rarely dissociates completely. So this conjugate base isn't just going to float around in water, staying as a conjugate base. It's going to react with water, according to this reaction right here, and create the weak acid and hydroxide because the water is going to transfer a hydrogen to it. And we don't know how much this is going to happen because the amount that happens is going to depend on the Ka. So it's a little bit different for every single weak acid that we're using. But we're going to start with 0.0500 because that is what we have here. Now this ice table is all in molarity. All in molarity, where this ice table was all in moles. And then we calculated the molarity at the end here. So we have a certain amount of the conjugate base at the beginning, right here. We don't care about the water, of course, in the ice table. And originally we have 0 and 0. And there's going to be some amount of change, negative on the reactant side, positive on the product side. So then we have at equilibrium, we have a certain amount minus x, and then plus x here. So in this equation, though, notice what x is equal to. This is x, and it's equal to hydroxide. So then we have to use the Kb. We cannot use the Ka for this weak acid. We have to find the Kb for its conjugate base, which comes with this equation. Remember that 1 times 10 to the negative 14, that is our special Kw constant. Ka of an acid times the Kb of its conjugate base is equal to Kw. So therefore, when you solve that, using the Ka we have at the beginning problem, Kb is 1.59 times 10 to the negative 10. We have this general reaction where Kb is equal to the products, x squared, over the reactants, which is B minus x, where B is the concentration of the original conjugate base. So we can ignore the x in the denominator here because it's so small that B minus x is still equal to B. So we ignore that, and we get this rearrangement. Then when you solve that, I would pause and solve it to convince yourself. X is equal to this, which, if you remember, x is hydroxide. So when you take the negative log of that, you get POH, subtract from 14, and here we have 8.45 for the pH of the equivalence point. All right, now we just have one more to find, and this is for after the equivalence point. I would pause and see if you can solve this. It's actually much simpler than you might think. Okay. So after we've added 30 milliliters of NaOH, we now have this amount of moles of hydroxide that goes here. This was our still original 25 milliliters of the weak acid. We have 0 of the conjugate base. Our change row now has to come from the number of the weak acid because the weak acid is the limiting reactant. So here's negative, negative, and positive, and we don't have any more of the weak acid. We just have a whole bunch of the hydroxide. So a buffer is when a weak acid is mixed with a strong base and the weak acid is in excess, but we don't have that anymore. We have a strong base in excess. So we don't have a buffer. You cannot use this equation. Please don't use this equation if you don't have a buffer. Notice my frustration. So the POH is solved by taking the concentration. Remember that this is the moles of hydroxide. Here's the volume. Our total volume now, this is the 25 plus the 0.03, or 25 milliliters plus 30 milliliters gets you 0.055 liters. moles divided by liters equals our molarity of hydroxide. So when you have molarity of hydroxide, you can find pH quite simply. POH is equal to the negative log of OH. So here's our POH, and then here's our pH, 11.96. So after the equivalence point is actually much easier, and you're not having, you don't have a buffer anymore, so you can't use the Henderson-Hasselbalch equation. You just solve the pH using the excess hydroxide. So what was that, 11.96 that goes up here?